so now I'm going to walk you through the proof of DeMoivre's theorem. Now, DeMoivre's theorem is used for powers of complex numbers. So if we have a complex number, a plus bi raised to a power of n, first step is we rewrite it, okay, as a polar form. Oops. So how am I going to do that without having to multiply out like, 10 times or whatever? So we are going to start out slow. Now, typically this is called a proof by induction, okay? Um, I'm going to walk you through kind of a simpler way to do it. It's kind of the same idea. You'll find that some of the notation that I use is a little bit different, but it's the same premise. Okay, so I have the multiplication theorem, okay, which says that z1 times z2 is r1 times r2, and it's cosine theta 1 plus cosine theta 2 plus I sine theta 1 plus theta 2. Okay, now, so that assumes that your z1 and z2 are different, but what if they were the same? So what if you were trying to find z1 squared? Well, your r's would be the same, right? And your thetas would be the same. So instead of saying theta 1 and theta 2, we could just say theta. Because everything would be the same, right? Okay. So now let's think about this. What's a quicker way to write r times r? Well, a quicker way to write r times r is just r squared. Okay, and then instead of saying theta plus theta, we could say 2 times theta. Just like that. Okay, so that's kind of the first step of proof by induction. You prove the simplest case first, which they usually call the k equals 1 case. Okay, now we're going to build from there. Okay, well, if I know that this is true for z1 squared, what would happen if I took and tried to find z to the third? Well, I could use z squared times z to the first. So that would be using the multiplication formula. Now remember, everything's the same modulus, same theta. So I'm just building. Okay. So now what's a simpler way of writing r squared times r? R to the third. What's a simpler way of writing 2 theta plus theta? 2 theta. Like that. Okay, so these are still specific cases. We want to take it to the general case. So if I do this enough, eventually what's going to happen is I'm going to assume z to the k is true. Let's try it for plus 1. All right, so what I'm looking for is zk plus 1. And if that's true, then everything behind it is also true. So according to my multiplication theorem that I've used a couple times now, r to the k times r to the first again, I'm just replacing my numbers with some integer k. And that's all I'm doing. So when you do a mathematical proof, you want to make it as general as possible. Because if you get too specific, it only works for those specific cases. So now, using rules of exponents, and I know this is a little strange. Basically, what you're doing is you're looking at previous generations of your formula and seeing if they're true, and then you're using it to prove a very general formula. Okay, so if this is true, then n equals k plus 1 is true. Again, this is called proof by induction. This is really rough, it's not very formal. Okay. Then we arrive at DeMoivre's theorem, which is actually a really cool theorem. Kind of makes life easier. Okay, and that's DeMoivre's theorem, and you've just proved it. So basically what you're doing is you're reusing the multiplication rule that we proved previously, and you're repeating it for the same number. Okay, remember, an exponent or a power is just repeated multiplication. So if we repeat it enough, basically what happens is we get to a very general formula for a power of z to the n. Okay, I hope that clarified things. Again, it's kind of new, and it's an interesting way to prove things. Okay.